Sir Isaac Newton, a famous scientist from the 1600s, formulated 3 basic laws to define motion. His laws, crucial to physics and everyday activities, explain rest, constant motion, accelerated motion, and describe how balanced and unbalanced forces act to cause these states of motion. But to see Newton's laws in action, we'll go out to the range to see these motions relatively exaggerated.
Out on the range, powerful forces act on projectiles, which make Newton's 3 laws very obvious, and the motions that are caused by them are extremely easy to observe. These motions are so complex and obvious that an entire field of physics is devoted to that study, ballistics.
Newton's first law describes inertia or momentum. Britannica defines the law as such.
Newton's first law states that if a body is at rest or moving at a constant speed in a straight line, it will remain at rest or keep moving in a straight line at a constant speed unless it is acted on upon a force.
Let's go out on the range to observe this law in effect.
Now this bullet is at rest relative to the casing. It will stay at rest unless acted on by another force. When I enable the explosive charge stored in the casing to go off by pulling the trigger on the rifle, I let a force act on the bullet, causing it to speed away from the gun, or the casing, which we're using as a reference, changing its constant speed, or in this case, rest.
Let's examine what just happened. Out on the range, we saw 2 examples of Newton's first law. On the range, I explained Newton's first law and how it worked when a rifle is fired. However, that same bullet can be used in our second example as well. A split second after the rifle is fired, the bullet comes in contact with the target. Our bullet, neglecting air resistance, travels at a constant speed after exiting the barrel. The bullet would have continued at this constant speed if another force did not act on it. The bullet collided with the steel. The steel acted on the bullet, and it changed the bullet's constant speed. This fulfills Newton's first law when the bullet's speed changed when another force was acted upon it. Newton's second law is often referred to as the law of acceleration. Wikipedia describes this law as:
a body acted upon by a force moves in such a manner that the time rate of change of momentum equals the force. The formula for this is F equals ma.
And this too is observable out on the range. When a trigger is pulled, a force acts on the bullet. This force is caused by the expanding gas created by the explosion in the chamber. Since this gas has nowhere to go, at least in this rifle, it pushes the bullet down the barrel, accelerating the bullet until it exits and flies downrange. Newton's second law comes into play here. This force from the expanding gas acts on the bullet. Let this be our force F. Our bullet weighs 10 grams, which is about 1 newtons, our mass. And finally, we can find out acceleration. At time 1, 0 seconds, our velocity is 0 meters per second downrange. At time 2, which is 0.0011 seconds, after exiting the barrel, our velocity of our bullet is at the highest it will be throughout its flight. An average 30-06 bullet fired out of a 24-inch barrel travels at 915 meters per second, more than 2.5 times the speed of sound, which puts our second velocity close to 915 meters per second downrange. So our change in time, delta t, is 0.0011 seconds, and our change in velocity, delta v, is 915 meters per second, which gives us an acceleration of 831,818.2 meters per second. Now, we can use Newton's second law to calculate the force acting on the bullet while inside the barrel. Our force F is equal to our mass, 0.1 newtons, times our acceleration, which we can round to 832,000 meters per second. This comes out to 83,200 newtons, which is a hefty blow dealt by our expanding gas.
Now in my original calculations, I assumed that the bullet would be stopped by the steel plate and therefore did all the calculations based off of that. However, in my live demonstration, the bullet passed directly through the steel plate. My calculations will work though for theoretical purposes, although in testing, the bullet went straight through. So
We can also calculate the force of our steel stopping the bullet. Since our bullet traveled less than 50 yards downrange, we can assume our first velocity is going to be 832,000 meters per second. Our final velocity, where the bullet is stopped, will be 0 meters per second. Since our stopping time is nearly instantaneous, we will use 1 times 10 to the negative 10 seconds, or 10 nanoseconds for our change in time. Our change in velocity is negative 832,000 meters per second. This means our acceleration equals negative 832,000 divided by our 10 nanoseconds, which comes out to negative 8.32 times 10 to the 14th meters per second. Now we can calculate the force acting on the bullet by our steel plate. Our force F equals negative 8.32 times 10 to the 14th meters per second times the mass of our bullet, 0.1 newtons, which is negative 8.32 times 10 to the 13 newtons. To relate these numbers to real life, having our bullet hit a steel plate mounted to your chest would feel like getting hit by a Prius traveling at 7 miles an hour. In short, it would be comparable to being run over because Priuses have terrible brakes. And now we get to take a look at Newton's third law, the law of reaction. Britannica writes this law as such.
When two bodies interact, they apply forces to one another that are equal in magnitude and opposite in direction. The third law is also known as the law of action and reaction. To put it simply, for every action there is an equal and opposite reaction.
In just the firing of a rifle, we can see 3 examples of Newton's third law taking place at the same time. When I pull the trigger on the rifle, the powder in the casing explodes, creating a pocket of expanding gas inside of the chamber. As this gas expands, it exerts pressure on 3 different locations. The gas expands outward against the chamber, which is our action, and the chamber is strong enough to resist that pressure, which is our reaction. Then the gas expands forward, pushing our bullet down the barrel. This is our action. But since the bullet does not push back against the gas, where did our reaction go? Our reaction is actually the kick of the rifle. When I fire the rifle, the expanding gas pushes the bullet forward in this direction, applying a force. That same exact force is applied in the opposite direction, which is the kick of the rifle into the shooter's shoulder. This action-reaction force is also used in automatic and semi-automatic rifles in order to oscillate the bolt back and forth. The force of the expanding gas, which pushes the bolt, allows for another bullet to be loaded into the chamber automatically. This can negate some of the kick of the gun simply by having a heavy bolt, which absorbs some of that reaction force. Although, a heavier bolt does tend to make the firing speed a little bit slower. Compensators are used as well to redirect the expanding gas so that the reaction force is pushed to either side of the rifle rather than at the shooter.
Although Newton's third laws are prevalent in everyday activities, they are exaggerated out on the range. Firearm designs, shooting, and ranges are all built around this exaggerated display of Newton's 3 laws.